when you put the electrons into their orbitals in those boxes, or even in the electron configuration, you have to start with the lowest energy levels first every single time. And this is called the Aufbau principle. So you can see here it's already set up this way, and the first electron goes in, arrow up. Second electron goes in, arrow down. This would represent the first box. Each one of these lines, you might as well, I mean, they can be the same thing as having a box right here. This is the Aufbau principle, okay? So then 1s, then 2s, then 2p, then 3s, then 3p, then 4s. You notice though that 4s then goes to 4d, then it goes to 4p, then 5s, then 4d, and that's based upon energy level. We'll talk a little bit more about that in the lecture in class. So how is this going to affect you for the AP exam? Well, what AP likes to do is they like to give you electron configurations or orbital notations and say, how are these violations of the Aufbau, Hund's, or the Pauli exclusion principles? So if Aufbau is they have to put one in the lowest energy levels first, what you might see is there might be an arrow straight up here in the 3s and nothing in the lower energy. Oh, you know, is this a violation of one of these three rules? And you say, oh, absolutely. It's a violation of the Aufbau principle. Careful, because they'll be tricky, because it could also be an excited state. An electron could be in an excited state. Okay? Now, and I've said in class, and I'll say it again, if AP likes to do it, I like to do it. So it's going to be on my test too. All right, second thing. Fill the orbitals each with one single electron before you can double up. So what that means is that if you put, like especially when you're looking at the p orbitals, if you put a single electron in the first orbital, you have to put an electron in the other two orbitals before you can add a second electron going down. All three have to have one before you can double up. If you're in the D's, all five have to have one before you can double up. This is called Hund's rule. So if you did this and you're like, oh look, here, I'm going to put one right here, and then I'm immediately going to put a second one right here, okay, right there, there is your violation of Hund's rule. So that is a big no-no, okay? Okay, and so there's not even an excuse for that one. That's not even, you can't even say excited. The last one is the Pauli exclusion principle. Of course, I have a particular place in my heart for this one. What will happen with this one is that you'll have two arrows going the same direction. Either they will both be going up, or you might have them both going down. And these are violations of the Pauli exclusion principle. So look for these on the test. That's all there's to know about those ones. All right, let's move on. So here are a couple of examples following the principles. Aufbau, fill the lowest energy levels first. Hund's rule, they're filling each orbital before they add a second one. And the Pauli exclusion, once they filled all three, they have electrons having opposite spins, positive half and negative half. After electron configuration is noble gas notation. Again, this should be review. So, real quick. Oh, I thought I changed this. Darn it, that's okay. Just look at this one up here. Ignore this right here. This is not there. Okay, here's neon. All right, that's a noble gas. Here's the notation for neon. Aluminum has all of neon plus it has 3s2 and 3p1. If this is in noble gas notation, you can take all of neons and put it in brackets and just put neon's symbol, the Ne, inside the brackets, and then that will count for all of the noble gas, and then just put whatever is additional for that element. Noble gas notation. Okay, ignore the rest of that. Oh, because that was argon and calcium. Oh, I see what happened. Never mind. Okay, moving on to quantum numbers. Quantum numbers can be a bit trickier. We covered these a little bit in honors chemistry last year. I don't know if we talked about them all this year at the beginning. They're covered briefly. I like to touch on them a little bit because they throw one or two in the multiple choice. I just want you to be prepared. And they're easy enough to understand. There are 4 quantum numbers. This slide gives you a lot of extra information. You don't need to know all the information on this slide. This is a lot of words and vocab and jargon. If you get it, great. If you don't, skip this slide and let's move on to the second one. Here, this is what's important. This is the first quantum number, and this represents the row. This is the second quantum number, and this represents the block. Okay? Zeros are S, ones are P, twos are D, and threes are F, which means in the S block, there's only, in that first row, there's only the S. In the second row, there's S and P. In the third row, there's S and P. And now, this third right here just means that in the fourth row, there's S, but remember that in the transition metals, you would drop an energy level. Okay, that's 3D when you write that electron configuration. So that's why that's a 3P's, right, or I'm sorry, 3D is right there. P, D, and F. Okay, so you have the first one's the row, the second one was block is it in. The third quantum number has to do with which orbital it's in. And that's pretty wide open. It really depends upon which block. If it's in the S block, there's only one possible orbital number. It's 0. That's it. Okay? Because there's only 2 electrons, 1 box, that's it. It's just the number 0. Okay? Imagine it like that. If it's in the P block, there are 3 possible. That's 6 electrons, right? Okay? Those are 3 of those squares, 3 of those boxes. You have 3 possible places. Now, I'm not telling you what order they go into. You just need to know that there are 3 possibilities. If it's D, there are 5 possibilities. And if there are F, there are 7 possibilities. Okay, so that's the third quantum number. The fourth quantum number is really easy. Okay, the fourth quantum number is basically the spin of the electron positive half or negative half. Positive half or negative 1/2. There's no way to tell that. It's one or the other. You are not going to be asked to write quantum numbers. You're going to be asked to identify a possible set of quantum numbers. You're going to be asked to identify if a quantum set of numbers is possible. If you were given a set of quantum numbers and your first number is a 0, is that possible? No, we don't have a row with a 0 in it. If you're given a set of quantum numbers and the first number is a 1, the second number is a 0, and the third number is a 3, is that possible? No. If it's in the S block, the only possible third quantum number you can have is a 0. Okay? So it's really just kind of like a little bit of a logic puzzle. They're pretty simple. You can see them on the practice test. If you have more questions, we can talk about it. Here's a little bit more about it that gives you just some more of the numbers that we just talked about. Okay. What I also wanted to mention, what we're doing here, is that there are the core electrons or the kernel electrons and the valence electrons. So in a situation like this, now I know they're doing electron configuration and noble gas configuration, which is a good way of looking at it. But these would be, for sulfur, these would be the core or kernel electrons. And these right here, of course, would be the valence electrons. And that's more of a terminology thing, just so that you're aware of. Now, what is most important about this slide is these 3 elements right here. These are transition elements. In transition elements, when you are making ions, the first electrons to be removed from a transition metal are the S block electrons, because they are the easiest to remove. So if you're looking at, well, and I say that, just included strontium, I'm sorry. We're looking at gallium and vanadium, not strontium, sorry. So you're looking at one. So gallium is going to lose, it's going to lose a P, and then it's going to lose its 2 S's, and it's not going to touch these 10 ones in the transition metal range because they are at a lower level. Okay, once they get locked in there, they start getting into a more, not lower, they get locked into a more stable level. Same thing here. The D, it's not that they're, I shouldn't say that they are outermost, but they're more stable. They're more stable than the S. And so what ends up happening is that, in this case, like vanadium can lose these 2 electrons first. So vanadium can form a 2+, or actually just, maybe I think it's just V2+, okay? Then it could lose the other 3 and form a V5+, but first it would do the 2+, it would lose the 2 of the S electrons before it loses the 3 of the D electrons. Okay, so it's going to lose the S and P's before they lose the D's. The D's are more stable, even though the D's are further out. It's a higher energy level than the S's. That's more stable. Okay, important to know. And again, we're going to talk about that periodicity. You can see a couple of exceptions to this. We start talking about when we're adding or taking away electrons for the transition metals. It's kind of interesting. Here we have, these are just the outer electrons, 3D1. So we did 4s2, 3D1, 3D2, 3D3, 3D5. Whoa, hey, how come that happened? We had 4s2s here, and then it took an electron from 4s2 and added it to 3D5. Again, it's adding stability. It'll give the D block greater stability to have 1 electron in each of its 5 boxes, in each of its 5 orbitals. Okay, the D block to have 1 in each of its 5 will give it greater stability, so it will take 1 from the S block. So chromium and copper are exceptions. These exceptions happen also. You're going to see molybdenum. You're going to happen to see it in silver as well. You also see it in gold. To make the D block more stable, it's going to borrow from the S block to fill, either get to a half-filled, every orbital is half-filled for the D block, or all the orbitals are filled in the case of copper, silver, and gold. Okay, and silver and gold are pretty darn stable as far as elements go. That's what we use them for jewelry, right? So these are some exceptions, and chemistry is the subject of exceptions. So those will, of course, come up later too. All right, last thing I think that I have on here that I want to talk about is paramagnetism and diamagnetism. And basically it's just this, and I'm going to kind of hustle through this. If it's paramagnetic, that means that the atoms with unpaired electrons in their orbitals are attracted to a magnet. Whereas if they're diamagnetic, they're all paired up. So paramagnetic, if you had a box, so if I have 1 in each one, they're unpaired. It's paramagnetic. Even if I had just 1 unpaired, it's still paramagnetic. The only way it's diamagnetic is if every single orbital has a pair of electrons. Okay? That's diamagnetic. Important to know. There'll be a question on the test.